So welcome back, grade 9 students, Advance. We are still in chapter 1, but this time we moved on to lesson number 4, and this will be our last lesson for this chapter. And here we go. The chapter started with identifying variables, or you can call it factors. In the previous lesson, yes, we considered as variables, something that it's changing while during an experiment. So when you perform an experiment, it's important to change only one only one factor at a time. So we can change two or multiple factors, but at this stage in our lesson for today, we are only moving or changing or modifying only one and only one variable. Okay, so if you look at this quick example here, we have a mass attached. So this is the mass attached to a spring. It's the same spring, but what's changing is the mass attached. So every time if I'm increasing the mass, what will happen to the spring? I'm controlling or I'm identifying the mass of the spring. That's what they are saying. I'm changing only the mass of the spring. So what happens? Sorry, the mass attached here in the red or in the orange. So what will happen? The spring will become longer and longer and longer every time. Okay, so simply I'm changing the mass here attached. So what will happen as well? The length of the spring will become longer. So let's take a look at it from this table here. So when, of course, when the mass attached, if you can look here on the first line, when the mass is attached, the length of the spring was, at first it was 13.7. Then when we increase the mass to 5 grams, what can you notice about the spring? It's becoming longer. Now it's 14.1. So you see this happens every time when increasing the mass from 10 gram, 15 gram, 20, 25, 30 till 35 gram. At the maximum, the spring reach a height or a length of 16.4 centimeter. So you notice at every stage the length of the spring is becoming bigger and bigger when we increase the mass. So the variable here, increasing the mass, another variable, so increasing the mass, that's what I'm controlling, I'm changing. Another variable is the length of the spring. So we continue. This is another example. So, but first we have to identify or differentiate between two types of variables. So you can look here. We have two types of variable. We have the independent and the dependent variable. Okay, no worries. So what do we mean by independent variable? So it's a factor that's manipulated during an investigation. So something that we are changing in our hand. Okay, in the previous example, it was the mass, okay, attached to the spring. So that's what do we mean by independent variable. So that's it here. Okay, that's what we mean by independent variable. Okay, but what can you notice? Every time we are changing the mass of the spring, what happened? You tell me the length, the amount of the spring stretched. Look at this sentence here. The amount of the spring stretch depends on the mass. So the amount of the spring stretch or the length of the spring is what? It's the dependent variable. So we have two things to learn here in this slide to differentiate between independent and dependent variable. Again, independent variable is the thing that I'm changing in my hand, and the dependent variable, what will happen to the experiment itself. Look at this example here. So what can you notice? At first we have, I'm watering the plant here. If I'm giving little water, okay, what will happen to the plant? It will stay small. The height of the plant will stay small. So that's what we mean by dependent variable. I'm giving water, okay, amount of water is what? Amount of water given is the independent variable. Okay, can you notice here? It's the independent variable. Here it's the dependent variable, the length. So look here, and on the second time, when I'm increasing the amount of water, that's I'm changing, I'm manipulating. This is the independent variable. Okay, the plant will grow bigger and bigger. So this is the dependent variable, the length of the plant. Okay, there are millions of examples as well on the dependent and independent variable. All right, those are the simplest one. So I hope you understand the difference between both of them. All right. So now we have two variables, okay, the dependent and the independent variable. Let's erase this. Okay, so again we have two types of variables as discussed in the previous slide, the dependent and the independent variable. This reminds us of the coordinate system, Cartesian coordinate, when we have one variable on the x-axis, the other one on the y-axis. So why not, remember the table that we discussed in the previous slide, we have a table. For every mass we have a length of the spring. For every mass we have different lengths. So we have two types of variables. So why not we can put them on a coordinate system as it's doing here. Okay, and then we draw a line. So for example, when the x variable was on 2, okay, the y variable was on 4. Okay, when it was on 4, the x variable, the other one, the y was around 6. So you see, for every x variable or for every value on the x-axis, we have a different value on the y-axis, and that's what we mean by line of best fit. So we draw, first step we put the points, as you see, first step we put the red points, and then we draw a line. Okay, if you notice the red line, the blue line is not passing by all the red, it's passing in the middle of them. That's why we call it line of best fit. Okay, that's why it's not only a line, it's line of best fit, because it's passing by most of the points but not all. Okay, if you notice here the point is a little bit above, or this one is a little bit below. So the line of best fit, okay, passing in the average or in the middle of all the points. All right, let's go back to this table here that we discussed in the previous slide. As I told you, for every mass or value of mass, we have different value of the length of the spring. So for example, if the mass was 5 gram, the length of the spring will be 14.1 centimeter. Then for every 10 gram, the length of the spring is 14.5 centimeters. So what to do in this case, how to draw this table? We have many steps. First step of all, we put the x and y system, and we put the origin in the middle, the point 0 or the point O. We put it in the middle, okay, of the x and y axis. Okay, then always remember this. On the x axis we put the independent variable. Here it is, the independent variable that I have it in the experiment. We put it on the x axis. Remember this. On the y-axis, we put the other kind of variable, which is the dependent variable, as you see here, okay, on the y-axis. So here, in this experiment, what do we have as independent variable? It's the mass. I'm changing the mass every time. So it was 5 gram at the beginning, then 10, 15, 25, okay? So what is the increment or the increase every time? I'm increasing it by 5 gram. Every time. So 0, 5, 10, 15, 25. So for every 5 gram, there is a value on the table. Okay, also on the graph. Okay, so that was for the x-axis. Okay, look on the y-axis as well. Again, as we discussed, it's about the dependent variable, but this time for every case or for every square, it's increasing, if you notice, by 0.5 only centimeter. Okay, so let's begin from here, 14.0, then 14.5, 15, 15.5, 16. So every time I'm increasing it by 0.5 centimeter only. You have to take notice of that. Okay, take note of that. All right, so again, first step, we draw the x and the y axis. Okay, the coordinate system, we point the origin, O. Then again, we put the independent variable on the x axis always, and the y. On the y-axis, we put the dependent variable. So now it's time to draw the graph. And on the next step, we pinpoint the black. Okay, so let's look the second one here. For 5 gram, it's about 14.1. So let's draw it for 5 gram here. Okay, 5 gram. Okay, the length of the spring is 14.1. So we put this green dot here. Okay, that is the first dot on the graph. Second value for 10 gram, here it is the 10 gram, the value is 14.5. So 10 gram, here it is 10 gram, it's about 14.5. So I draw a second point here. So now we have 2 points. Okay, and you continue with all the points. Okay, then on the next step we draw this line here. So this line we draw it when we to connect the points, and that's what we call by line of best fit. Okay, so again I'll repeat the steps. First step, we put the x and y axis, we put the origin, we put the independent variable on the x-axis, the dependent variable on the y-axis, of course with taking into consideration the steps every time. Here for every one case or one square, it's increasing by 5 gram. Here for every 1 square, it's increasing 0.5 centimeters. You have to take note of the units as well. Okay, so for every 1 square, it's increasing by 0.5 centimeter. Okay, then based on the table, we draw the black points on the graph, and then we draw last the line of best fit. Great. Let's move on to the next. All right, so we have different types of relationships between x and y and between dependent and independent variable. Let's start with the easiest one. It's about linear relationship. So from the name we can consider that linear, it's coming from the word line. It's a line. It could be this way, it could be horizontal, it could be vertical, it doesn't matter. The only thing that matters, it's about a line. It's linear relationship. Okay, it is a line, and this is an example of a linear relationship between x and y. All right, so when we have a linear relationship, the equation, I assume you studied this in math as well. So when we have a linear relationship, the equation, the mathematical function will be this way. It will be m multiplied by x plus b. Okay, so we have one variable which is on the y-axis, okay, which is the dependent variable, and we have the second variable which is on the x-axis. Okay, so this relationship that exists between dependent and independent variable, okay, in terms of a linear relationship. Okay, now what we have to calculate, we have to find out the m every time. What is m? Okay, what is the value of m and what is the value of b? So when we find out the value of m, which is called the slope of the line, I guess you studied this in math as well. When we calculate the value of m, which is the slope of the line, and also we have to calculate b, which is called the y-intercept. All right, let's calculate m on the first step. So the value of m is calculated according to this equation. Let's make it bigger. So the value of m, which is called the slope, okay, if you notice here, it's called the slope. So m is equal of any linear relationship, m is equal the change on the y-axis. So m is equal to the change, means delta, change of the y-axis, divided by delta on the x-axis. So how the y change, delta means change, so the change on the y-axis over the change on the x-axis. Okay, and that's what we call by m. So let's take an example based on what we learned on this graph. So you can take any two values, change of any two values, doesn't matter. You can change, you can take this point or that point, or this point here, or this point, any 2 points on the line, any 2 points, you can consider them. So here in this example, they consider 2 points only. So as well, so they choose when the y-axis is on the 16, okay, so they took, I think, this value here, this one. Let's make a circle on it. Sorry, here. Okay, so they took this value here, okay, and they took the other value, which is 14.1, I guess that one here. Okay, so they took these two values, so this one again, okay, and the value here. So look how they did it. So remember, it's delta y over delta x, means the change means m will be equal to y2 minus y1 over, remember delta is the change, the difference means the difference, that's why we put minus. So y2 minus y1 over x2 minus x1. You can call it initial final or initial a and b, it doesn't matter. Okay, I call it 2 and 1. Okay, so look at the values here. What is the value of the first y here? Here the value is 16, so they put 16 minus, okay, so this is here it's y2 minus y1, so they consider this as y1. So y1 in this case it's 14.0 or 14.1, so minus 14.1 over, now we come to the x, we have to look on the x-axis again for the first point. So for this point, what's the x of this point? It's 30. Okay, so we put 30 minus, what is the x of the second point, which is 5. Okay, so you do this on the calculator and you get the value of 0.08. What's the unit? It's centimeter. Okay, it's centimeter, here the length over gram. Okay, remember the units of the graph, so it's centimeter over gram, and that's how we calculate the slope. It's the difference on the y-axis over the difference on the x-axis. So now it's time to calculate the b-intercept. So we calculate on the first step the slope, which is the m. Now it's time to calculate the b value, which is the y-intercept. So the y-intercept b is the point at which the line crosses the vertical axis. Okay, which is, what do you mean by vertical axis? It's the y-axis. So look at this line again. We follow this line. At the point when this line crosses the vertical axis or the y axis, we call it the b-intercept. If you notice here, the value, it's around something between 13.5 and 14, so it's considered as 13.7. So the b in this case it's 13.7, as you notice here. Okay, so that's what we call by the b-intercept, this point. So now what's the equation? What's the full equation now that we have it? So remember, y is equal mx plus b. So now the equation of this line, remember the value of m, it's 0.08 multiplied by x plus, what's the value of b? It's 13.7. Okay, that's the equation of this line. Okay, something to note here. What if this line, imagine this line passing by the point 0, not that like that one. Imagine we have another line that's passing by the point 0 this way, any line passing by point 0. It could be this way or that way, it doesn't matter. If it's crossing the point 0, so in this case the b-intercept will be equal to 0. We don't have a value for the b-intercept. The y-intercept. So the value of b in this case, as you see here, the b will be equal to 0. Why? Or when this happened? When the line passed by the origin, by the point 0, 0. Okay, great. Another type of relationship. So we finished with the linear relationship and we studied the equation y equal mx plus b. We have a different type of relationship exists between dependent and the independent variable, which is called the non-linear relationship, and we have under it we have the quadratic relationship. Okay, we have the quadratic relationship. When we have a quadratic relationship, every time we don't have a line, it's about a curve, as you see here. It's not a line anymore. You see the curve, and also the type of equation change. Now we have a square root of 2, okay, to the power of 2. The power of 2. So y equal ax squared plus bx plus c. Okay, now it's about power of 2. So that's what we mean by quadratic relationship. Okay, it's not a line, it's a curve. We have also another type of relationship. It's called the inverse relationship. When the x-axis move on opposite to the values of the y-axis. They move in opposite way. So what kind of equation we have this time? So it's about y equal a over x. Okay, that's that kind of inverse relationship. So every time you have this type of equation when a is over x, so you have to know it's about an inverse relationship. Let's give an example about that. So look at this here. First, we have to read the title of the graph, relationship between the speed and time. So the speed is on the y-axis, on the x-axis, it's in kilometer per hour. So you see from 60, 65 till 100. Okay, so we are increasing the speed. So every time the speed increases, what will happen to the time travel? So let's say if I'm moving at the first value here is 35 kilometer per hour. I'm moving too slow. So it took me like 8 or 9 hours here travel time. It took me like 9 hours to reach my point. If I'm moving faster like 60 or 70, it's taking me like 4 hours, only 4 hours to reach my destination. If I'm moving at 100, so you see the value of the x-axis increase. So I'm moving on the 100, but the value on the y-axis is only small, it's only 3 hours. So you see, when the speed increases, the time decrease, and that kind of, this is an example of inverse relationship. When the speed increases, the time decrease. Okay, let's solve this question together. All right, so we have question with the table given. So let's read it together. We have the mass value of a specific volume of pure gold nuggets are given by this table, table 4. Okay, plot mass versus volume. So plot means to draw. Okay, so we are about to draw the graph based on what? Based on this table that we have here. Okay, so first step, as discussed, we put we draw the coordinate system, the x-axis, and we have the y-axis. We put the origin in the middle here. Okay, so what do we have as on the x-axis? It's about the volume. Okay, the volume this time is about the x-axis. Okay, what's the unit? It's given by centimeter cube. Okay, on the y-axis it's the mass. It's about the mass, and it is expressed in gram. Okay, so let's look at the units or at the values of the x-axis. Let's move this time. Okay, so we have the volume, which is in centimeter cube. Okay, let's look at the volume 1, 2, 3, and 4. So let's divide the x-axis according to 1, 2, 3, and 4. So these have to be equal to equally separated. So 1, 2, 3, and 4 centimeter cube. Okay, that's for the x-axis. On the y-axis, we have also divisions. So it's 19.4, it's around 20, 38.6 around 40, 58.1, 27, 77, and 96. So it's around, like, for every one case, it's about 20. So here 20, here it's 40, here it's considered 60. Okay, can you see? 60. Here is 80, let's consider, and here is the 100. Okay, I avoid putting the decimal, the comma, just to make it simpler. Okay, so 19.4 based on 20, close to 20, 38.6 close to 40, and this way. All right, so we put the value on the x-axis, the value on the y-axis. Okay, we divide the axis into the values. Now it's time to connect them together. So if the volume was 1, so if the x is equal to 1, y is equal 19.4. So for 1, it's around little bit less than 20. So it's somewhere here. Okay, 19.4. That's for the first point. Second point, if volume is equal to 2, so the value is 38.6, which is close to 40. So 2 it's around 40 or less than 40 by a little bit only. Okay, that's for the second point. For the third point, if volume equal to 3, it's about 58.1. It's close to 60 as well. So this is a 3 and this is 60, a little bit less than 60, so it's supposed to be this way here. Okay, if the volume is equal to 4, it's 77, so it's around a little bit than 80, so this way. And for 5, so it's somewhere here, this is 5, it's supposed to be around 100, so it's 96, so it's less of 100. So these are the points. So let's draw a line. So these are the points. Now it's time to connect them together. So we have to connect all these points together. Okay, we have this line. Okay, this is what you call by line of best fit. Okay, I have to work on my writing skills and my drawing skills, but this is the line. Of course, use the ruler and it will be better or more net than this. But anyway, you are getting a line similar to that, and that's how we draw the mass versus volume from the given value in this table. Okay, and this is the line of best fit. Again, I remember you that the line of best fit should not pass by all the points, but by the majority of the points, or the average of these points. Okay, describe the resulting curve. So what do you see? It's like a direct line. Okay, so it's not a curve, it's a line. Okay, this leads us to question number C. According to the graph, what type of relationship? Of course, what do you think about this relationship? It's linear relationship because we are getting a line. It's a linear relationship exists between the mass and the pure gold on their volume. So the relationship exists between the volume and the mass. In this case, it's about a linear relationship because it's a pure line. Okay, what is the value of the slope of the graph? So this is question number or question D. What is the value of the slope of this graph including the proper units? So now let's calculate the slope. Okay, remember when we have a linear relationship, we have to draw or to write this kind of equation, which is mx plus b. So in this question, question D, they want us to calculate the value of m. Okay, what is the value of m? Okay, we don't know yet. Okay, so how did we calculate it in the, remember, how did we start by calculating? So m equal the change of y, remember, over the change of x. So let's take any two values from, you can look at the graph, but to be more exact, you can look, because my drawing is not like perfect, you can look at the table here. You can take any 2 points. Let's take the first 2 points. So or let's take the last and the first point. Okay, so it's 96.5. That's the value of y. Remember, the mass in gram, it's the y-axis. Okay, so the mass in the y-axis. So I take this value, 96.5, and the first value. So this is y2 minus y1, which is 19.4. You can take any 2y, you'll get the same value. You'll get the same thing because it's linear relationship. It doesn't matter where you choose the points. So I choose the last point, which is 96.5, and the first, which is 19.4. So y2, this is y2. Can you see? Minus y1 over x2 minus x1 again. Okay, so what is the x of 96.5? It's 5. It's 5 centimeter cube minus the first x minus x1, which is 1. Okay, so 96.5 minus 19.4 over 5 minus 1 means 4. You do it on the calculator. Let's do it on the calculator together. So we'll get the value of, you can do it with me, 96.5 minus 19.4 divided by 4. So the answer is 19.4 let's round it, 19.3. It's 275, but let's round it, 19.3. And what would be the unit? Okay, so it's a gram over, remember it's y-axis over x-axis, so it's a gram per centimeter cube. All right, okay. Right, so now with the last question, write the equation showing the mass as a function of volume of the gold. So they want us to write the equation. So they want us to do this equation. So y equal mx plus b. M already calculated. It's 19.3. Now we want to calculate the b. So what is b in this case? Okay, so this is b here. Okay, we calculate the slope. Okay, so now what is b? So b is the question, the y-intercept. Look again at the graph. Here we need to look at the graph. Remember what I told you in the previous slide? If we have a line passing by the origin, so what would be the y-intercept in this case? So y-intercept in this case, it will be equal to, so the b is equal to 0 in this case. Why? Because the line is passing by the origin. So let's write the equation again. So y equal, okay, y equal, which is the mass, okay, so the mass equal m, which is 19.3, can you see 19.3, x, okay, y equal mx. So what is x in this case? The volume. So mass equal 19.3 multiplied by the volume. Okay, so and that's the equation. Mass equal 19.3 multiplied by the volume in this case. Great. Let's clean the board to move on to the next slide. Okay, predicting values. So this is very important. In math and in physics, we predict values. So what's the point of writing an equation, y equal mx plus b? Okay, so we are predicting using this equation. Remember that it could be linear relationship or quadratic or even the inverse relationship. We can predict values. Remember the graph that we draw, x equal 1, 2, 3, 4, 5. What if the volume will be like 10 or 20, it's big value, or 100, let's say? Can we draw it on this graph? Yes, we can, but it will be not exact. So we have to use predicting values using the equation. So even if the x, remember the previous equation where y equal 0.08 centimeter gram plus 13.7, okay? What if x equal to 100 or 2 or 1000, let's say, okay? So we can predict values using this function or using this equation. So here, if x is equal to 49 gram, what will be the value of the length? Okay, it will be 18 centimeters. So no need to do the experiment, no need to draw the graph. Okay, so it's about putting the value on the x-axis, or here in the x function, and then we get the value on the y. And that's what we mean by predicting value. Okay, we are predicting what this value will be equal if x is equal to this number. Okay, so here is another question. Yeah, it's also about the drawing. So graph means also to draw. Plot, all will have the same meaning. Graph the following data. Time is in the independent variable. So remember, so we always start by putting the x-axis and the y-axis. We put the origin here. Okay, what they are asking, they want the time is the independent variable. So they want the time to be here on the x-axis. What's the value of time? 0, 5, 10, 20, 25, 30. So it's a division of 5 seconds every time in seconds. Okay, so this is 5, let's say 10. You can use the ruler, so you can use it, make a drawing better than mine. So 5, 10, 15, okay, 20, 25, 30, 35. Okay, so for every division it's about 5 seconds. What about the speed? Okay, you see we have a value of 2, 4, 6, 8, 10, 12. So also we can divide it based on, let's make every division equal to 2. Okay, so this is 2, that's 4, that's 6, that's 8, that's 10, that's 12. Okay, so what's the value? It's a speed. Here on the y-axis we have a speed expressed in meter per second. Okay, so graph, they want us to make a graph. Okay, so that's the first part. We draw. Now we have to draw the line of best fit. So if time is equal to 0, the speed is equal to 12. So that's the first point here. Can I use a different color? Let's try this. It is different. Let's see. So if the first value is 0, time is 0, the speed is 12. If the time is 5, the speed is 10. So 5, 10. Here is the second point. Is it different? Seems different. No, it doesn't matter. If the time is 10 seconds, the speed is 8. So here it is. If the speed is, sorry, the time is 15, the speed is 6. Here. So you see, it seems like going down. You can tell from here, even before drawing the line. You see the values are start to go down. For 20 seconds, the value is 4. Okay, for 25, the value is 2. And for 30, it's about 2 as well. So here it's a straight line, I guess. And for 35, it's 2. So you see, it's about going down. This is the line of best fit, going down, and then it's a straight line. Okay, I mean it's a horizontal line. Okay, so it was going down, and then we have a straight line. That's how we graph this table. Okay. Here, interpret a graph. So what would be the meaning of a non-zero y-intercept in a graph of total mass versus volume? This is an interesting question. Let's give an example. So let's make a QG graph, x and y. What would be the meaning of a non-zero? Non-zero meaning, so 0 is here. Let's say the y-intercept starts from here, let's say. Okay, that's what we call by b-intercept, this point. Okay, of a graph of total mass versus the volume. So let's say here is the mass and here is the volume. Okay, what this graph means? This means that if the mass is 0, and you tell me if this is possible or impossible. Look at this and you tell me. This is origin O, this is the origin. This graph means if the mass is equal to 0, this is non-zero y-intercept, by the way. If the mass is equal to 0, the y-intercept, which is the volume in this case, have a value. I don't know, it's maybe 5, 10, I don't know, any value. 5, 10, it doesn't matter, but have a value of a volume. So this is possible. An object have a zero mass, have no mass, but have a volume. Is this possible? I don't think so. Okay, I repeat, the y-intercept is dangerous in this mass and volume graph. Why? Because it means that even if a mass of an object is 0, okay, it's at the origin here, it's 0, the y-intercept have a value. It could be 5, 10, 100, it could be even 1, doesn't matter. So, is this possible to have a 0 mass but still have a volume? That's not possible. Okay, that's how we interpret this graph. This graph could not be true. Alright, let's move on. We are doing great job. So, going back to this graph. So we have this question, yeah, we're about to finish. So Predict using the relationship illustrating in this figure to determine the mass required to stretch the spring 15 centimeter. So what would be the value if we stretch the length of the spring by 15 centimeters? So let's look at this. So this is 13.5, 40, 40.50. So that's the line here. Okay, can you see? So if we stretch the spring by 15 centimeter, what would be the value? What might be the value? It's around also 15 or 15.1. Okay, so that's how, based on the graph, we can tell the value in this case. So if it's 15 centimeter, so it's based, it will be around 15. Yes, it's around 15 or 15.1 gram. Okay, or you can consider it more than that. All right, so but anyway, that's how we connect the 2 points. So we draw the horizontal line and then the vertical line. Okay, we continue. Okay, so use also, it's similar to the previous question, use the relationship shown in this figure, figure 18, to determine the travel time when the speed is 110 kilometer per hour. So this is also about predicting the value. It's about predicting. Here in the graph, let's erase this. So here in the graph, we don't have a value of 119 kilometer per hour. The maximum one that we have is 100. Here it's 90, 95, 100. We don't have 110. That's why they are saying predicting, because it does not exist in the graph. So how this graph can continue in your opinion? So we reach this point. Now it will continue as horizontal. Okay, so if we continue this graph, it will take this shape. Okay, it will take this shape. It will turn as a horizontal line. Okay, this way. So if it's 100 here, 100 is about like 3 hours. Okay, 105, it's also about 3 hours. 110, because it's reaching a horizontal line. Okay, it will also be like, it will go and touch the 3 hours again. Okay, you see, it's about 3 hours again. So that's how we can predict based on the graph. We are predicting the values, I mean. All right, critical thinking. Look again at this graph. We have this graph again. Let's clean the board. Okay, so look again at the graph in this figure. In your own words, explain how the spring would be different if the line in the graph were shallower or had a smaller slope. So we have this graph, this famous graph that we are studying since the beginning of the lesson. What if we have a different line? We don't have this line. What if we have, they are saying, a smaller slope. A smaller slope means M. The M is slower or lower. Okay, so slower M or slower slope means we have, let's say we have this kind of line. Line is lower. Okay, or could be this way. Okay, or that way, it doesn't matter. But we have a slope less than the main one here in the blue. So what would be the interpretation in this case? What do you think? This means that the spring is stronger. Why? Let's show you. For the main, remember, always refer to the main one. Here is the blue. Okay, the main one. Okay, for every 5 gram, remember, for every mass of 5 gram, for every 5 gram, 5, 10, 15, it's increasing around 0.5 centimeter. Okay, as you see in the graph. If I'm drawing a smaller slope line, for example, let's consider this one here. Okay, this means if I'm increasing by 5 gram the mass, 5, 10, 15, 20, 25, the spring, the length of the spring is not moving a lot. It's moving, yes, but little bit compared to this one. You see, if I'm moving 10, 15, 20, 25, the y value changing, delta y, is small. You see, it's small, it's getting smaller and smaller. Here the change is bigger in this line. It's here, it's 14.5, now it's 15, now it's around 15.5, now it's around 16 I mean. All right, so however here the value for let's say 15, it's like 14.3. the value for 20 gram, it's around 14.5. So you see the change in the y, in the length of the spring, is becoming lower. Okay, so how this will be interpreted when we have a smaller slope means the spring will become tough. We have a tough spring because the spring is rigid, is not moving. Okay, it's very difficult to move to stretch the spring, or you can write it will be difficult. It will be more difficult to stretch the spring. Okay, it become tough to, even if I'm changing the mass, increasing the mass, it will become more and more difficult. Okay, but here, however, here it's more easier to stretch the spring. Now it's 15, here it's 15.5, 60, 16.5. all right, and here's it's around 70. Okay, so for every 5 gram here on this line, it's a little bit difficult to stretch the spring. I think that's it for lesson 4. Thank you for listening, and we'll meet you again in chapter 2.